Um,
All right, so have you guys talked much about KSPs at all in class?
Yeah.
Or have you discussed it at all yet?
We already did.
Yeah, we already had finished the chapter with it.
Okay, so you guys should feel pretty comfortable with doing some KSP calculations.
Yep.
So let's talk about the solubility. Oh, such I'm missing letters. Product constant. And what symbol is given for that solubility product constant? What's like the
SP.
Yep, ASP. Okay, so what this is, what does this describe? Like, what's the purpose of KSP? What physical information do you get from it?
How soluble a compound is.
Yep. So it's a constant to describe solubility. Okay, so if you have a low KSP value, what does that mean about your solubility?
it's not very soluble.
Right? The lower the value of KSP, the lower the solubility. So, oh, except I'm missing an L. There we go. So a lot of times you'll hear the term, you'll hear insoluble, but a better way to describe this is sparingly soluble. Geez, this camera sucks. You can do it. All right, let's try that. There we go. So the question we're going to ask is why is sparingly soluble? A better term than insoluble. So let's say we have a solution. There's some water here. We'll do it in, I don't know, say it looks green. Someone tell me an insoluble salt or a sparingly soluble salt. Like, give me an example of one.
Lead chloride one.
Yeah, lead chloride. Okay, let's say we take some lead chloride and we throw it in the bottom there. So we have some actual physical lead chloride, that kind of cool yellow color. We drop it into our water sample. What's going to happen? Like, what's happening at this like really small molecular level? Is all the lead chloride just going to stay as a salt? Like, it's just going to stay solid, nothing else is going to happen?
A little bit might break off.
Yeah. Yep, there's a small amount where we reach an equilibrium, where we get lead and then 2 chlorines. But then what's happening to these guys that are in solution?
Deposit back into lead chloride.
Yep, they're going to go back and forth. So we've reached an equilibrium that way. So if we introduce some lead chloride into a solution that has originally no lead, eventually we'll detect some levels of lead in there. Now it will be really small. Lead chloride is considered insoluble or a sparingly soluble salt. Why is it better to use the term sparingly soluble rather than insoluble? Anyone have any suggestions or ideas?
Because insoluble is like, it doesn't dissolve at all.
Right. And what do we, and in reality, what do we know about this salt?
A little bit dissolves.
Yeah, it's really small. For some of them, it might be like really, really tiny, and that's what it is in this case. But still, there is some that's dissolved in solution. So despite having most of the solid undissolved, a tiny amount is dissolved in solution. So that's why a lot of the times when you're like looking in your book and you're reading, you'll see sparingly soluble over and over again. Okay, does that make sense to people? Okay, so let's look at an example of using KSP and determining some concentrations. So our example, we're going to determine the concentration of chromium in a saturated solution of chromium 3 hydroxide. Okay, let's first determine what we're trying to answer. What question are we trying to answer here? Or what are we looking for?
Concentration of chromium.
Yep, we're looking for that concentration of chromium. Okay, what words in here are important to us? What do we need to know? What helps us?
Saturated solution.
Yep, saturated solution. Okay, what else?
Chromium hydroxide.
Yep, chromium 3 hydroxide. Okay. Where should we start with this problem?
Balanced equation.
Okay, balanced equation. So what do we need a balanced equation for?
Dissociation
Yeah.
of chromium hydroxide.
Yep, so chromium 3 hydroxide, we need the dissociation of that. What is the formula for chromium 3 hydroxide? Bringing you back to Gen Chem 1.
CrOH3.
Yep. Okay, so this is going.
Like, wait, isn't hydroxide like one thing?
Yep.
Oh,
So what am I missing?
the parentheses for the.
Yeah, I need parentheses here. There we go. Okay, and it's dissociating. So what do we need on the other side?
Chromium and then hydroxide. Or 3 hydroxide, I guess.
So we need 3 of these. What else do I need in here?
Charges.
Yep, charges. What's the charge on the chromium?
+3.
Yep. Hydroxide?
Just minus.
Yep. Now, we also need to indicate physical states. What's the physical state of this guy?
Oh,
Yep, solid.
yeah.
And then these other two?
Aqueous.
Aqueous. Some professors choose not to have you write out that aqueous. It's kind of implied that it's there. We're going to write it in our case just so it's there. But no, if you don't want to do it, you don't have to do it. But check with your professor and see what they do. Okay. All right, so we got that. What do you suggest we do next?
Don't we need like more information, like a KSP or?
Yeah, we need a KSP value. So we need a KSP of this chromium 3 hydroxide. So where would you find that information?
Probably the textbook.
Yeah, I would check the textbook. Google does have some of them, but a lot of times the numbers that they spout out are incorrect. It just can't seem to figure out those chemical formulas for some reason. So I would highly suggest to either look in your book or look up like a KSP table online. So if we do that, I think the value is 6.7 times 10 to the minus 31. Okay, what else do we need?
The hydroxide concentration.
We would need the hydroxide concentration, but what it told us is that we have a saturated solution of this guy. So we actually don't need the hydroxide ion concentration. That could help us out a ton.
You make a rate law, right? Or
Not rate law, because remember, equilibrium.
sorry, yeah.
Yep. So what? Not rate law, but what were you thinking? I think you
Just like
yeah, like a
concentration of chromium times. Sorry, that's my dog.
That's okay. He's excited about equilibriums too. So we got KCr3 plus. What else do we need for our KSP expression?
Hydroxide cubed.
Yep. All over what?
Nothing.
Not why nothing.
Because the chromium hydroxide is a solid.
Yes, exactly.
Like
The
chromium
physical
hydroxide.
that physical state makes a big deal. Remember, what types of physical states get excluded from the equilibrium constant? We said solids and what else? Pure solids.
Gas as well.
Gases actually do get incorporated. They can also be like partial pressures or concentrations. So we talked about solids, gases. What's the last one?
Liquids.
Yep, pure liquids. Pure liquids get excluded from the equilibrium constant. Okay. The reason for that is these things are all like what we're looking at are changes in delta G, or explicitly what's known as chemical potential. In pure liquids and solids, their chemical potentials don't change. Therefore, they're excluded from the equilibrium. That's more complicated than you probably wanted to know, but that's why it's there. Okay, so now we got all the makings we need to figure this problem out. So what do you suggest we do next? Or what do you always do with equilibrium type problems?
Nice table.
Yeah, ice table. So let's do that. ICE. We only have two things in our equilibrium constant. We have chromium 3 plus and we have hydroxide. Okay, what does the I stand for again?
Initial.
Initial. So what's the initial concentration we have here? Or are we going to pretend that we have?
Do we not have an initial? Because
Yep.
it's.
Yep, keep going. What were you going to say?
Do we not have an initial because they're products?
Yes. So we're going to assume in this case, we took like a little bit of solid, we plunked it in the water. Before anything could dissociate, we have nothing in the solution. So we're going to say 0 for our initial. Okay, C, what does the C stand for?
Change.
Change. Okay, so we can define these in any way you want, but they have to be in molar ratios to one another. What do you want to call, let's start with this one. What do you want to call that guy?
X.
X. Yep, okay, let's go X. Is it going to be a positive or a negative value?
Positive.
Can anyone give me a reason why?
It's a product.
Yeah. Well, and we're starting with 0 of this, right? We can't get to a negative concentration mathematically and physically. That just doesn't make any sense. Okay, so the change is plus X here. What should the change be for the hydroxide?
Plus 3x.
Yes, exactly. E, what does the E stand for?
The equilibrium concentrations or final
Yep.
concentration.
Yep, our final concentrations or equilibrium concentrations. So what should these values be?
For now, just x and
Yep.
3x.
Exactly. Okay. Because what you did, you just took the initial plus the change, that's the equilibrium, right? In this case, since the initial is 0, our life's easy. Okay, what do you suggest we do now?
Plug it into the equation thingy.
Okay, let's plug it into this equilibrium equation. So we got KSP is equal to X 3x cubed. Okay, what now? Let's combine these terms together. So KSP is equal to X. What's 3x cubed equal to?
27x cubed.
Yep. Okay, combine this together. What's this become?
Twenty-seven x to the fourth.
Yep. Okay, now what are we solving for in this problem?
X.
Yeah, we're looking for X. Okay. So what would we do to isolate X by itself? What's it going to be equal to?
The fourth root of
Mhm.
the KSP over 27.
Yep. Like that, right?
Yeah.
So we can plug in numbers. Oops, I'm going to do that on the next page. So we got X is equal to KSP divided by 27. So we got 6.7 times 10 to the minus 31 divided by 27. Value should be 1.3 times 10 to the minus 8. Okay, so what does this X value describe again? Looking back at our ice chart.
How much dissociated?
Specifically what?
Ca3 plus.
Yep. So Cr3 plus is equal to 1.3 times 10 to the minus 8. And what's my unit on this?
Molar, like molar.
Yep, molar. That can sometimes be implied with these brackets. I like to put it on there just so I don't lose track of it. Now, did we answer our question?
What was the question?
So,
Yeah.
we did, because we determined the concentration of chromium. I'm going to tack on one more thing though. Let's pretend we wanted to know the hydroxide ion concentration. How do we do that?
Multiply
What were you going to say?
multiply it by 3.
Yep, multiply it by 3 because this is equal to 3x. So it's 3 times 1.3 times 10 to the minus 8. So in that case, 3.9 times 10 to the 8th molar. Okay? Everybody feel pretty comfortable with that? Okay, so what you're going to be doing today is you're going to be using ice tables. You're going to be doing you're going to be using data from a titration to figure out a KSP value. Okay. So let's answer some of the pre-lab questions, or one of the pre-lab questions. What is the goal of today's experiment?
Find the KSP
Yep,
of the
what was it?
the calcium iodide.
Yep, iodide. So what were you using as, so you have 3 parts, or there traditionally are 3 parts in this lab. Part 1, what's the purpose of part 1?
So we know how much solid we're starting off with.
Yeah, so basically make solid. Okay, part 2, what's the purpose of part 2? Or what's the title say?
Standardization of the EDTA solution.
EDTA. Okay, so what is, you don't have to tell me the chemical formula for EDTA, but what is EDTA? Like, why are we using that? Or what is it?
Binds with calcium.
Yeah, it binds to calcium. Actually, it's pretty cool. It looks like Pac-Man trying to gobble something up. Or have you ever seen like an octopus like go over something and eat it? This ligand, it's a multidentate ligand, meaning many teeth. And what it does is it binds and bites into that calcium, which is pretty cool. So the word standardization, what does that mean again? Because in the
Like
past,
find the concentration.
Yep. So we want to know, we want to be sure of the concentration. Because later on, we're going to use this, we're going to titrate this with an unknown. Or we're going to use it for an unknown. Part 3, what are we doing in part 3?
Determine the calcium in the calcium iodide.
So basically, you're taking, what you're going to do with, well, what you would do is you would make that solid, you would isolate it, then you would throw it into some solution. From there, just like we discussed with that lead chloride at the beginning, we have some amount of solution. We'll introduce the calcium iodate we made, and then some of the calcium and the iodate will go into solution. Then we're taking an aliquot, or a little bit of this solution that we've allowed to get saturated, and we're determining the calcium 2+ concentration using the EDTA. So if you look in your lab report, or excuse me, the lab manual, there's like an equation number 3, basically where you have your EDTA plus your calcium 2+, and you get an overall charge of 2-, but these two interact with one another. What's the molar ratio of these? Like the molar ratio of EDTA to calcium?
1-to-1.
Yeah, 1-to-1, which is really beneficial. It makes the math much easier. So the data that you guys have, you have part 2 data where you're trying to determine the concentration of the EDTA. In part 3, you're using that EDTA to determine the calcium 2+ concentration. Now, how does that help you figure out the KSP value? So what is the KSP expression for this solid? Or can anyone tell me the equation for dissociation for this guy? Let's do that first. So what's this calcium iodate going to dissociate into? Any
CA.
ideas? Yep.
CA plus 2
What else
plus-
we got?
plus 2 IO3.
Yep. Okay, somebody else, tell me the KSP expression.
Concentration of calcium
Mhm.
times concentration of iodate. Is that cubed or squared?
Squared. Yep, exactly. So just like we did in our example, you can kind of construct an ice diagram and you can figure out, okay, if you know your calcium concentration, you can figure out your iodate concentration. And from that, you can determine a KSP value. Okay? Everyone feel like they have an idea of what they're going to be doing today. All right, this is the first remote titration I've ever done, so we'll see how it goes. Are there any questions at all? No?